Hello, everyone. My name is Xuemin Shen from the University of Waterloo, Canada. Today, I'm going to give a talk on reinforcement learning for resource management in space, air, ground integrated vehicular network. It is well known the main concerns of the current transportation system are safety, congestion, and the environment. For safety, global road traffic crashes account for 1.2 million deaths per year, top the cause of deaths for ages 15 to 29, and 3% of GDP loss for low, middle income countries. For congestion, commuters waste 8 billion hours in traffic per year and $160 billion loss due to urban congestion. For environment, wasted fuel is topped 3 billion gallons, in addition to 56 billion pounds of CO2. To address those challenges, the potential solution is the connected vehicles. Vehicular communications networks have attracted a lot of attention recently, not only from the academia, industry, but also governments, due to its significant impact to our daily life. V2X means to make vehicle exchange information with everything, including vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian, vehicle to cloud, vehicle to sensor, etc. With the V2X, information such as vehicle speed, location, road conditions, etc., can be exchanged among neighboring vehicles so that road safety can be significantly enhanced, since drivers can get early warning so potential vehicle collisions could be avoided. In addition, congestions can be relieved due to better traffic management, such as traffic light control, street light management, intersection movement assist. Transportation systems become more environmental friendly since vehicles spend less amount of time on the road, so that less CO2 emissions will be released. Furthermore, V2X can bring many other applications, such as smart parking, on-road entertainment, EV charging management, location-based services. However, the challenges are V2X communications require a lot of wireless resource due to large amount of data traffic. This is because V2X communication is a typical heterogeneous machine and human type coexisting communications. Currently, each vehicle has about 50 to 100 sensors, and this number is expected to be doubled in the near future. The data traffic generated by the sensors is about 750 megabits per second. In addition, human-type traffic data keep increasing due to the requirement of on-road infotainment and location-based services. In addition, the vehicle high mobility and unreliable channels make it difficult to satisfy the strict quality of service requirements of different vehicular services. In addition, some human driving behavior, such as fatigue driving, distracted driving, under-influence driving, aggressive driving, are very difficult to be managed. Therefore, recently, automated driving has attracted a lot of attention. That is, using machine to replace human to drive vehicle. From a system point of view, for human driving, the input of driving system is the information of road environment obtained through eye observation. Then the driver takes actions based on the observations, the driver's driving skills and experience to control the car, including speed, braking, and the steering, etc. For automated driving, the road environment observation is conducted through high technologies such as camera, lidar, sensors, etc. In addition, the collected driving behavior data, GPS, and high-dimensional maps with the observations are used for the machine computer to make automated driving decisions. Although the automated driving related technologies has been highly developed, automated driving still face challenges from the technical, legal, and the marketing aspects. First, hardware limitations. The detections of radar, lidar, and optical cameras have their own constraints in terms of range, sight, and the weather conditions. For example, the camera cannot work if the sight is blocked by a truck ahead. Second, software reliability. Due to the hardware constraints, such as CPU and storage, the processing capability of the automated driving is constrained. In complex situations, the software may crash and cause huge loss. Also, the processing capability is constrained by the training data and the experiences. In special cases, the software may fail and make wrong decisions. For example, it cannot detect and deal with the temporal constructions not posted on map or database. In addition, software may also be attacked by hackers, causing security and privacy issues. Third, the automated vehicles also face other issues such as legal and marketing problems. High price, as the automated vehicles require advanced hardware embedded, like laser radar, HD 3D camera, the automated vehicle will be much more expensive than conventional vehicles. Also, people who like to drive for fun may lose their hobby, while people who drive for work may lose their job. In addition, government may have lots work to regulate the automated driving, including detailed liability when accident happens. Since the automated driving mainly depends on the computer vision to learn the driving environment, there are also many challenges due to confusing traffic lights, bad weather, fading lanes, etc. Those challenges can be overcome through V2X, since vehicles can get the global information of traffic and make global optimization together through vehicle cooperation. This can greatly improve sensing ability, accuracy, reliability, as well as traffic efficiency. In other words, V2X communications can help to make automate driving safer and easier. On the other hand, sensing intelligence can help to reduce the V2X communications workload, enhance communications reliability and efficiency. Since automated driving vehicles can obtain a lot of information locally, which can significantly reduce a lot of V2X information exchange. In addition, local message sensing is more reliable due to less transmission delay and potential communication attacks. With less message sharing, the privacy can be better protected. Also, automated driving is more regulated and can be controlled. Therefore, if the engineers and the researchers from both V2X and the computer vision can work together, the automated driving based on communications, computing, and the sensing will become safer, more convenient, clean, and a better cooperation. The Society of Automotive Engineers of America has proposed the 6th level of automated driving. In level 0, there is no automation. The human driver performs driving all the time. In both level 1 and level 2, the human driver are required to monitor the driving environment, and the driving assistance system acts passively. In level 3, 4, and 5, the automated driving system monitors driving environment, and the driving assistance system acts actively. Currently, most research and development are on the level 3 and the level 4 self-driving. There is still a long way to achieve level 5 self-driving or full automation. To achieve level 5 self-driving, there is a long way to go. This is because full automation requires seamless network coverage for service continuity. In addition, robust, flexible resource management is required in order to ensure sufficient resources during rush hours and special events. This slide shows two maps. One is a Canadian map, one is a China map. The challenging is that the network coverage is very insufficient. From those two maps, the areas with color indicates that there is network coverage. We can see that in Canada, the network coverage is only about 20%. And in China, it's less than 40%. This is due to many reasons, such as cost, offshore, mountain, etc. Also, the vehicle traffic depends on time, such as rush hours, location, such as downtown area, special events, etc. The solution for the future full automation vehicle is the space-air-ground integrated network. The space-air-ground integrated vehicle network means to integrate the satellite, area network, and the ground network to provide any vehicle, anywhere, anytime communications. Our objective is to build a space-air-ground integrated vehicular network which is responsible to enhance the coverage and the vehicle mobility. One, the UAV or the drone can form moving cells to keep pace with the movement of the vehicles to provide flexible capacity for special events during rush hour. Satellite is responsible for location and navigation and also covers the area without ground network access. This slide shows some commercialized equipment for satellite with vehicle communications. Also, different industries around the world, in China, US, UK, have put a lot of efforts to achieve the air and the ground network integrations. The main issue related to the space-air assisted networking is how to make efficient use of different networks resources to support services with a different QoS requirements. This figure shows our proposed hybrid and hierarchical control architecture of the space-air-ground vehicular network. Hybrid means satellite, UAV, and the ground network for urban and remote areas. Hierarchical control means local access control plus central resource allocation control. With this architecture, the local controller collects the individual vehicle service requirements through the roadside units and the available ground network resource. It passes the information to the central controller. The central controller makes the resource allocation to support individual vehicle services with certified QoS requirement based on the overall available network resource from satellite, UAV, and the ground networks. We propose to use SDN controller for resource management in space-air-ground vehicular network. The SDN controller enables network slicing of virtual networks so that different SAGVN services with diversified QoS requirements can be effectively supported in the independent virtual networks on the top of a shared physical network infrastructure. For the SDN controller, there are two inputs. One is from the demand side. One is from the available resource side. The SDN controller makes the decision what type of resource and how much of it will be used to which service. Due to the high dynamics of service demand and available resources, this decision is based on the reinforcement learning. For reinforcement learning, an agent in this case, network controller, learns the best policy through interaction with the unknown network system environment. At each system state, for example, UAV location, the agent takes an action, observes the reward, for example, pass load throughput, from the environment to know how good this action is, and adjust its future action based on the reward. Therefore, reinforcement learning learns the best policy, that is, which action should be taken at each system state for resource management. We have developed reinforcement learning-based SDN controller to efficiently manage SAG resources. By interaction with environments, the decision map of the SDN controller can be obtained offline. In this way, the resource allocation decision can be done in real time according to different service requirements, which is very suitable for vehicular scenarios. With the SDN controller, we can do adaptive access control, which means for a vehicle on the road with a service requirement, the controller can decide which resource will be used to support its service requirement. The SDN controller can also decide the number of UAVs needed and each UAV's trajectory in order to maximize the UAV coverage ratio and the network throughput. In the following, I'm going to present the Space, Air, Ground Vehicular Network Simulation Platform. Currently, there are available software for space, air, and ground network simulations. For example, STK is a software package to perform complex analysis of space platform. VSIM is an advanced and flexible traffic simulation software with complex vehicle interactions, mobility, traffic planning. However, there is no simulation platform supporting the integration of space, air, ground vehicular network functions. Since this platform is urgently needed to promote the research and the development of space, air, ground vehicular network, we use related simulation softwares to build the platform. In specific, VSIM and STK are used to generate the physical object, location, and the mobility of network nodes, including satellite, UAVs, and the vehicles. Network Simulator 3, or NS3, runs the core simulation. And the Python and the MATLAB are used to develop interface to further extend the capability of the platform. Here is an example from the simulation platform. We choose University of Waterloo campus as the simulation area. By selecting a testing vehicle, the SDN controller can decide which resource and how much of the resource will be used to support the vehicle based on the available resource, number of vehicles on the road, and their service requirements. This is an example of the access control from the simulation platform. In this scenario, the asset control is performed to maximize the achievable network throughput of the testing vehicle. It can be seen in the animation with multi-dimensional mobility introduced by vehicles, UAVs, and satellites. The testing vehicle can be served by different network resources at different times with a time-varying achievable throughput. In the following, I'm going to introduce the SDK System Toolkit simulation tool to simulate the satellite communications. Originally created to simulate Earth's orbiting satellites, SDK provides highly comprehensive parameters and the data of existing LEO, medium Earth orbit, or MEO, and GEO satellite systems. SDK can be utilized for data analysis, and it also provides visualization tools. We can also configure the satellite simulation scenario and the corresponding communication parameters, including power, antenna gain, path loss, etc. in SDK. Notice that for the satellite orbiting information and the locations of satellite ground stations, we can either import from the existing database or customize them by ourselves. The simulation results from SDK include access time, signal-to-noise ratio, bit error rate, etc. that can be obtained with the built-in analysis tools. In this slide, by setting up the different simulation scenarios, we can observe the satellite access time and the communication performance in terms of signal-to-noise ratio and the BER. The satellite access time refers to the time duration within which the satellite can establish communication links with the ground users. The access time depends on the orbit of the satellite. In this slide, the two figures show the BER performance comparison between LEO satellites and the MEO satellites. It can be seen that MEO satellites have larger access time due to the height, while LEO satellites have better communication performance in terms of BER since it's close to the ground. We simulate two Beidou medium orbit satellites and one Beidou inclined orbit satellite. The simulation results shows the individual satellite access time. By considering all three satellites together, the overall access time in a given location is more than 90%. In these slides, we demonstrate the development of UAVs to support vehicular users in a dense scenario. The SDN controller decides how many UAVs are needed, which trajectory each UAV should follow for a given scenario. In the figure, there are 5 UAVs. The left figure is the 3D view, and the right figure is the corresponding bird's eye view. The small squares represent the vehicles, the solid circles represent the UAVs, and the black triangle is the base station. Vehicles with different colors are served by different UAVs according to their service requirements. This figure shows the animation of the 5 UAVs trajectory. Here are some parameters and the scenarios considered in the simulation. Here are some related work from our research group. In the first work, we present a network slicing-based network architecture for the next generation wireless network, the motivation, research challenging, and the potential future direction related to applying AI-based approaches in the next generation wireless networks are described in details. In the second work, we propose SDN-based space air ground vehicular network control framework, where a hybrid and a hierarchical SAGVN control architecture is proposed to manage the resources, including communication, caching, and computing from different network segments. Furthermore, AI is utilized to design resource management algorithm to address the difficulty in system modeling and enhance resource management efficiency. In the third work, we present our developed SAGVN simulation platform, which supports the space, aerial, and the terrestrial network and the communication functions to facilitate efficient network management in the SAGVN. Centralized and decentralized controllers are implemented to optimize the network functions such as access control and resource orchestration. In addition, various interfaces enable flexible functionality extension in the platform to facilitate user-defined mobility traces and control algorithms. In conclusion, space air ground integrated vehicular networks can support diverse vehicular services efficiently and cost effectively anywhere and anytime. The presented network architecture can achieve network agility and flexibility and simplify network management. There have been significant efforts in the development of SAGVN. How to efficiently and effectively orchestrate communications, computing, caching, and control resource is a very important research subject. In addition, more attention should be paid for vehicular services which require different security goals such as authentication, confidentiality, and integrity. Thank you.